Welcome to a conversation about using co-packaged optics to create next-generation AI architectures. I'm Timothy Prickett-Morgan of the Next Platform. Thanks for joining us. I think we should start by having everyone introduce themselves, talk about what skin they have in this CPO game, and what their aspirations are for it. And I'm going to start for once. As a sports writer for the data center, I've been talking about smashing servers into bits and gluing them back together for composability. I was thinking electronically at first. Now the dream for me is optics. I want to be able to break memory free of compute. I want it to be able to be in trays and racks, and I can upgrade it separately. I've wanted this for a long time. And if we ever get there, I think I can retire because my work here will be done. So let's have everybody else talk about this. Vladimir, let's start with you.
Vladimir Stojanovic. I'm a CTO and a co-founder of Ayar Labs. Kind of founded the company with that similar dream of optics really solving the bandwidth problems of compute at scale. And we're right now in the middle of it and really trying to get the optical I/O and into the compute packages, memory, the switch packages, and to build the highly performant AI systems.
Okay, thanks. And Erez, tell us about yourself and what you think.
My name is Erez Shezaf. I'm Alchip CTO. And basically in Alchip, we are building like, I would say, the biggest AI accelerators. And we are facing like the wall of the I/O bandwidth. And I believe that together with CPO and with Ayar Labs, basically we can break out this I/O bandwidth wall and improve the system efficiency from many aspects. So it's really like a very nice journey to build up this kind of new technology.
All right. And Audit, finally you. Let's have you explain who you are.
My name is Adit Narasimha, and I lead an emerging technologies business group at Astera Labs. Yeah, smashing the server sounds extremely dramatic. And so our view of it is that if you look at next-gen AI architectures, the unit of this heterogeneous computing is really the rack. Okay? And there are two very critical sockets in this rack. One is the accelerator and one is the switch. Okay? And our flagship product is a switch to wire all these GPUs together. And we do believe in scale-up networks. If it can be copper, it will be copper. But at some point, this thing is going to go optical. Okay? And it will go to optical in a kind of holistic way, all the way from model metrics to demanding, let's say, a larger domain size to larger egress densities. And that's what will demand optics at that rack level. And that's our skin in the game. So we're very interested in how that plays out and how we can eventually get to that roadmap point of how our switch is optically enabled.
With that out of the way, let's dig in. We had silicon photonics in the scale-out networks for a long time because you can't push a signal over a wire without a lot of repeaters. And there's just too much energy involved in that. So at some point, we came to another transition that we could not avoid. And that's how we got it in the scale-out network. Right now, we're seeing it emerge, co-packaged optics, or CPO, because I'm going to start saying CPO, it's easier. It's starting to be embedded onto the switch ASICs. And frankly, it's because it's easier there. The volumes are lower. The need is greater because you can't get from the switch ASIC out to the front panel on copper anymore. So they've already hit that limit without having a lot of retimers, repeaters in there. So, and then eventually I think we will get it in the interconnects onto the compute engines, and then we'll have maybe CXL memory and optical interconnects as well. So that's kind of the evolution that I see and others see. Let's start and talking about, is that a reasonable progression? And Audit, we'll start with you. What do you think? Is that a reasonable way to expect it to evolve over the next couple of years?
Yeah, I think so. It's interesting you bring up scale-out networks. Scale-out had the advantage that it lies in a domain where this bandwidth distance product, it absolutely demands optics. Okay, there's just no doubt that you need optics. So that in confluence with in confluence with customers that are able to provide very high volumes, it's resulted in very good cost, performance, and availability of scale-out networks. Okay, so that is a mature kind of commoditized space. Okay, but it's actually worthwhile comparing scale out to scale up. Let's say on three pillars. Okay, one of them is technology. Okay? When you look at scale up, we are talking about some significant densities relative to scale out. In scale out, we're talking about 4 lanes or 8 lanes. You can easily fit that in an OSFP or a QSFP-DD module or what have you. In scale up, we're talking about many lanes, which means customized PHYs, which means new modulator technologies, which means new coupling technologies, okay, and which means new tightly co-packaged technologies. Okay, so there's clearly a technology piece that's different from scale out. The second piece is the advanced packaging flow and testing piece. In scale out, you're developing a mechanical, thermal, optical, and electrical interface to a chip. So every module maker, as it were, is capable of doing that in their own way. Okay, whether it's clumsy or not actually doesn't matter at the end, as long as you have a reliable product. In scale up, it really matters, okay, because there's a huge interaction of that packaging and test flow with its eventual integration into the switch or the CPU, as well as its eventual integration into the rack. And then the third piece is the supply chain. Okay? Do you really have a supply chain and an ecosystem that is mature and sustainable enough to deal with the enormous volumes of scale up? Okay? I would argue that the first one, which is the technology piece, the proof of concept has happened. Okay, I think the concept has been proved. There are many companies that have shown various modulator technologies. I think this feasibility stage has kind of been crossed. Okay, and some people may debate this, but I do believe that. The second piece, which is the whole manufacturing and test flow and advanced packaging flow piece, I think that is debatable as well, but I believe that is less mature. Yeah. And I think
you're getting ahead of me. This is the whole rest of the talk.
So I think that piece still is left to mature. And then the third piece, which is the supply chain piece, I think that hasn't happened yet. Okay. So from that perspective, scale out is offering a kind of protective environment to prove out this CPO stuff. Okay. It doesn't have the pressure that scale up puts on the ecosystem problems and the advanced packaging flow problems, but it's sort of a proving ground and a pipe cleaner for CPO. So I think the way you stated your progression is correct, but as an industry, we have to work on all these 3 pillars. I still regard the first one as decently done. It won't matter in the end whether it's a Ring or an AM or a Mach-Zehnder. Okay, but the second and third piece of this packaging flow and testing and integration, plus the supply chain piece, are what will eventually make this happen.
Vladimir, I see you nodding your head a lot, so you go next.
Well, yeah, I mean, look, we do.
Don't give all the answers to all the questions in one answer.
Exactly.
Okay, you have me a break here.
Yeah, I think definitely share the opinion that the scale out is really a proving ground for kind of the next 1 to 2 orders of magnitude higher level of difficulty, which is scale up, and then, as you mentioned, extended memory connections, both in terms of bandwidth. We're talking about 10 to 100x. In terms of the volume, supply chain difficulties, and also the stakes, because you are now getting closer to the highest BOM item in the whole AI system, right? And you have to be that much better in yielding all the assembly, and actually also at the scale that is also 10 to 100 times larger, right? So that is definitely something that's currently first and foremost for us as a company to be able to enable that backend. I also share Adit's view that we largely demonstrated that the technology works. It works in those environments that are required. We do believe that rings are the right technology to get the density, especially coupled with advanced 3D stacking that's coming out, for example, from TSMC in their COUPE technology, which allows you to really leverage the size of rings to shrink all the transistors and circuitry that you need to shrink. Because, as Adit mentioned, you really need to up your game in density when you're getting into the scale up, as well as the extended memory. We're talking about the bandwidths coming out of a single chip that are already at the level or higher than HBM bandwidths, right? So that's no small thing.
All right, Erez, you're coming at this from the other side. You're actually helping people build the compute engines I'm going to lead to the next question. Why do we need CPO on the GPUs and the XPUs? Why can't we just use InfiniBand forever and be happy?
So first, we should be happy no matter what. That's not the way.
If any of this works.
So I think that there is time for evolution and a time for revolution. I think that in the last so many years for me in the industry, like starting from 1 gig SerDes going to 10 gig, and then 25, 40 really didn't catch up, and then to 56 NRZ, 56 PAM4, and later on the 112 PAM4 and 200 PAM4 and so on. We see evolution. What does it mean, right? So evolution means that basically we do more of the same. We are actually bringing more layers to the package, and we are trying to actually squeeze more bandwidth on copper. And basically, when we are doing the package design or we are trying to get more bandwidth, every time the job becomes like harder. For example, signal integrity with PAM4, it's much more harder compared to NRZ, right? Because we have so many more level inside the SerDes. And basically, when we are dealing with PAM4, the power integrity is crucial. Otherwise, the SerDes will not work efficiently, or we might have too many bit error rates and so on. So now, what we see in the market is actually that this AI accelerator, the pace in the market for like a new generation is like 1.5 years. Every 1.5 or maybe 2 years, there is a new generation and people would like to push more bandwidth. If you look on the SerDes, right, SerDes are not progressing so fast, and the adoption of like new materials and additional package layers required much more time than the pace of this accelerator in the market. So basically, instead of like doing evolution, meaning going from 6 layer in the package to 9 to 12 to 14, we are trying something new. We are trying to bring optics, which by native, it's much more like a better channel, much less losses, less parasitics. It's bring, of course, like different kind of challenges, but I think that because of the pace and because that we are talking about like the scale up network, which is more like a protected environment. It's not like the scale out in which you need to be interoperate with so many vendors and so many unknowns, because we would like to build like a definite system. I mean, we would like to build a rack solution or maybe like multi-rack solution. I think that the problem is very well defined. And because of that, and because of the pace, then this is the time to go for the CPO. That would be my take on that.
All right. Vladimir, what do you think?
No, look, I think that's exactly right. If you look at these types of systems, you need technology that has a multi-generational potential. Just as I was saying, like copper was that for the last 25 years. And, remember around 2000s, there was a whole transition into SerDes and equalization, and all that was like scary from like what was happening in the 90s. That transition was made, and you had like a couple decades of exciting roadmap. We need a technology now in AI systems that has that potential, and that is exactly CPO. If you go look at the technology, how much we can scale through which degrees of freedom we have, number of wavelengths, the modulation rate, number of ports per chiplet, meaning the connector density, polarization states, etc. Down the road, you have a lot of generations that you can do once you're coupling the technology that has a density potential, like micro rings with advanced transistors. You have that potential for multi-generational kind of system development, and that's what's really needed, because you are investing all the other stuff around it. As Adit was mentioning, the supply chain, the connectors, the way you test, the way you attach, all that equipment and capex has to be rolled in, and it's not going to get rolled in for 1 or 2 generations, right? It needs to get rolled in for a form factor that has at least 2 decades worth of potential. Otherwise, that investment will never get recovered.
It sometimes feels like we're going to have to compress 10 years worth of development in 5 years. This is how fast this hockey stick of AI and the demand on the rack scale system is. What do you think about this? Do you think that, we can build something today and start building that foundation and then it will go for 10 years, or will we have to do something a little more dramatic X years from now? And, 1 or 2 or 3, it's not 10, and kind of break with the past a little bit more and take a risk.
No, I 100% agree with Vladimir about investing in multi-generational technologies, right? That's pretty easy to agree with. The second thing I do agree with is that, this kind of integrated photonics in a dense co-package has that multi-generational potential. Okay? Now, the question remaining is, what is the true transition point, right? And your readiness on those 3 pillars that were mentioned before are very important. But additionally, I think it's not prudent to take an existing technology and say this is its state and then compare it to the future of an incipient technology. Yeah, you have to also project the existing technologies forward and say, what are they going to do to counter it, and what will actually move the transition point out in time? Okay? Because existing technologies not only have their benefit of being proven on a technical level, they successfully create enormous inertia throughout the entire value chain. Okay, people want to stay with what they've done before. People want to use what they've done before. People want to realize the value of their sunk investments, and so we do have to be responsible about projecting the existing technology forward, whether it's different forms of optics or denser connectors that will enable density for modules in order to correctly try to position the transition point. But from the perspective of this space needing a technology that is multi-generational, as well as this being a very strong candidate for that technology, no doubt.
And you guys are building opposite ends of this thing, so it has to come together too, right? Does there have to be a sort of standard for the interoperability? Can we have different optical engines from different suppliers and different optical engines that are created by the compute engine makers and the switch makers? And can we make this all work together, or is it going to be a little crazy for a while? I guess that's the way I would say it. Erez, I'll start with you.
Let's start looking on the UCIe, right? There was a very big promise about like UCIe is going to have like interoperate between dies, between technology nodes, between foundries, between different kind of package and so on. But at the end of the day, UCIe is just a name for like a parallel bus, a file layer. And basically, I think that today we are facing that UCIe is like the Wild West, meaning everybody take it and do like a different flavor with different optimization, whether for the bandwidth, whether for the power, or whether for some other reasons for the packaging. And I think that it's really depend with the customer landscape, meaning if you're a big customer and you have enough volume production and you can control the supply chain, why would you agree not to get the best for you? Why would you go after standardization, which may make your life easy, but on the other hand, there is a penalty with standardization. Committee, time to market, and sometimes the solution is not optimized for you and so on. Mm-hmm. So basically, I would say that there is a room in the market for optimized solution and a customized solution, and also for standardization. But I think that the big CSPs will go with what is the best for them, which is not necessarily following like any standard in the market. They will just use their enormous, I would say, capacity to actually tune the vendors and ask for customization based on their needs, which might not be like the standard one.
Interesting.
Yeah, and maybe maybe like a slight variation on that is, look, as Erez pointed out, these scale-up systems are closed kind of systems, right? In a sense, and I would even say that what's very plausible is having some sort of a small MSA kind of thing where you have multiple suppliers do something that's kind of a very similar optical engine, which will be deployed essentially. One cluster is one type of engine, another cluster is another type of engine. But as long as everything else in the form factor in the supply chain is shared, right? Whether it's exactly modulation compatible and has like a fraction of a dB here or there, I think that's going to be less of an issue. As long as you can actually leverage the downstream assembly, test, and supply chain, because these big deployments will look for the uniformity in that aspect. Nobody has, except like a few big companies in the world, has the pool to essentially go and set up, hundreds of testers or thousands of testers, and also like connector assembly machines and things like that. That's where actually I think the foundry ecosystem will provide, essentially, think of it as a certified OSAT ecosystem that will be preferred. And being in that ecosystem and following that process, and having a solution that is actually the right form factor to follow that process, I think is going to be key. Whether you have one more bump on your chip or not, and things like that, I think will be allowed deviations. But you have to follow some chunk of the process with that form factor. Otherwise, it will be too much investment would be required to kind of stand that up as a separate solution, and also to integrate it into the whole compute package.
I think, the historical trend for CPUs was everybody invented their own NUMA architecture, their own NUMA chipset, but because it was isolated to a motherboard and it was just traces on a PCB, they could get away with doing whatever they want. With CPO, it isn't like that. You're not just laying things down on a trace on a motherboard, and now you have to have the light pipes. There has to be some sort of compatibility between them. So I think that will compel people to do things that are compatible. But I understand that there are you pick the number. Once OpenAI starts making its own processors and systems, are there 7 big customers who can do whatever they want, whenever they want? Yes, there are, and they represent more than half of the market. So I'm saying it's hard to predict this. It's hard to say if they're going to work together for the benefit of economics and maybe speed to market, or if they're going to focus on differentiation that's specific to them and their applications that they're running on this AI hardware. Otto, what do you think? I'll let you finish that part.
I think all the comments are very valid, and there were some implicit thoughts in there. The first one is our customers will determine what happens. Okay, so we have
that's for sure. Yes,
yeah. So and you just made that point. We absolutely acknowledge that. The second one, I truly agree with that. If you and I think this was implicit in some of the remarks. If you choose to I say standardized, but it's really also achieved by an MSA, which is more efficient in terms of time and so on, and even optimization of specs. We have to choose the right interface to do it. Okay, what is the element that is really multi-sourced? If you start doing it at the wrong point, then you truly have a suboptimal system. Yeah, so it might not be practical to say, let me just have a pick from anybody on Earth. Okay, that doesn't work. Then you start to say, can I have a chiplet from anybody on Earth? Maybe that works, but then you have to standardize everything on the die-to-die side. If you go down the road of let's standardize the entire optical interface, you get into what has happened in scale-out networks, which is nice interoperable modules that are still somewhat power-hungry. Okay, so I think the choice of what's the exact element or level of, let's say, system construction to standardize is very important. I do agree with Aris that in the beginning, the whole benefit of the scale-up network is that you can allow for innovation to occur to truly optimize the outcome for what is needed. And I think if we get deep into standardization, that will hold us back on that front. Yeah. So we really need to strike the balance of what our customer truly wants, enabling multi-sourcing for them at the right, let me call it the level of abstraction, and treating it as a system problem.
I think it might end up being a lot of protocol differentiation, some differentiation on a number of lanes of, CPO interconnects that people use, and maybe a couple of different types. And that gives enough flexibility and still allows for some commonality so we can ramp up volumes, get good manufacturability, all that stuff. I mean, I don't think there's going to be 10 different ways to do it. That doesn't make sense. But there may be 10 different flavors of 3 different things or whatever, I don't know. Who's going to, let me ask a trick question, or at least an interesting question. Who's going to go first on, and you don't have to name names, but we'll just keep them in buckets. Is it going to be one of the indigenous, chip suppliers? Is it going to be one of the hyperscalers or cloud builders or model builders that's developing their own ASICs with the help of companies like Alchip and Broadcom and Marvell? Who's going to be the one who lays down the CPO on the CPU or the XPU first? Vlad, you go first. Don't out any customers.
That's right.
But just generally, who's going to do it first and why? I would have argued, and then I'll let you have this thought. I was pretty sure that NVIDIA might go first with Rubin, and then I was just sorely wrong. I was just way wrong. I think Jensen must have copper futures or something. I don't know.
Well, look, I think the race is on, definitely, and I think the window is becoming very, very clear of when this is going to happen. Look, the verticalization is apparent, right? There's a couple of organizations that have verticalized quite a bit, and what is also apparent is that the pace at which the cloud or the hyperscalers are adopting new technology has also accelerated. I wouldn't say it's accelerated to the point where they're leading the charge, but they're, I would say, much closer to kind of immediately following than in previous technology insertions and things that were happening. If you look at like CPUs and things like that. And you also have the third kind of stool, which is some kind of starts of some sort of an open ecosystem that's trying to form, that's a more open access than the full vertical, right? And why is that happening? Because the hyperscalers want to eventually build stuff in something that's more or less an open ecosystem, not to be completely captive to a one vertical, right? And I think that's kind of the landscape currently. It is very strategically interesting, and also how much this AI pool is really accelerating all the thinking around it.
Mm-hmm. Erez, what do you think? And again, you can't out your customer, right?
Yeah, I think this is a very interesting question, and in order to answer that, I would like to take a step backward and look at the landscape of the scale-up network, right? So today in the market, I think that we have like maybe 3 or 4 flavors, right? Not a secret, like we have the NVLink, we have like ESUN or SUE coming up, we have UA-Link, and we have also like the PCI Express, which is considered to be like a cheaper version of like a scale-up network, but very efficient on the other hand, very easy to deploy. So we see at least like 4 flavors at the moment. So I think that once a customer choose a path, they will stick with that because it's involved like the ecosystem, the hardware, the software layers, and some other important features. So I think that I would think that one of the hyperscalers will go first with CPO in order to bring like more, I would say, benefit to the selected scale-up network in order to keep pushing like how many GPUs can be integrated in under like one scale-up network. So I believe that would come from one of these guys.
All right. My bet's on Google. They've got an optical switch with a million little mirrors twisting around. Why not put CPO on the TPU and see how that works out? But I don't know anything. No one's told me anything. I haven't heard anything. Amin Vedat might tell me someday after it happened 5 years ago. Otto, what do you think? Who's going to go first?
I think I agree with thematically what was said. Who will go first will be the one that can look at it in terms of the need for it all the way from the top down, plus the ability to pay for it that is justified by that need for it. Okay, because I don't think people should think that this is going to be the same price as copper. Okay, that has never been a good way to compare stuff. So clearly you have to pay for it correctly, and that'll be justified by the actual need for it, which then translates to the larger domain sizes that is alluded to, which translates to the larger egress density that Vladimir alluded to. But that whole equation, the person it works for first will actually pay for it and make it happen in terms of true customer pull. And then everything will move quite quickly after that.
All right. Well, we've talked about the compute engines. I want to talk about this extended memory thing for a little bit. I think 2 or 3 years ago, Vladimir, we talked with a bunch of people, and I think I was with a bunch of other people talking about how I don't really care what the underlying, communication is. I want it to be optical, and I do want it to run CXL. I don't care how you do it. I want the extended memory. I want to be able to, have trays of memory that are remote and yet still have high bandwidth to get back to the compute engines. And then I can change my tray of memory forever and ever, as I see fit, and use it forever if I see fit too. So, how is this going to evolve? And what has to happen before that becomes more normal? That's a much bigger ask, I think, than it is to have some light pipes coming out of the CPU or the GPU and going out to the switch and then, creating either a scale-up network or whatever. I think this is harder. So talk to me about CXL extended memory over this.
Yeah, look, it's definitely a harder problem because it's also latency is also much more constrained than in the scale-up network. Although, some scale-up networks are becoming very aggressive in targets. And why is that the case? I would say currently because of the copper bandwidth limitations, you have very few paths through a scale-up network. And what happens then is that the queuing latency in the switches actually dominates. So there's no much incentive to shrink the latency of the copper link because the switch dominates, right?
Mm-hmm.
However, if you add a lot of paths, meaning you provide a lot of bandwidth to a scale-up network through optics, all of a sudden, through path diversity, you can drop the switch queuing latency to a minimum. And that allows that kind of, then the link latency sticks up. And that allows you to kind of optimize that as well. And of course, optimizing the latency overall in the scale-up network does lead to faster AI and also more users. So it improves both throughput efficiency and interactivity, right? So there's some room.
Think about how much better NUMA would have been we might have actually had 128-way NUMA that worked.
Yeah, look, bandwidth and latency were always trading off, right? And optics allows us to break that trade-off and does allow some optimization of the latency in the scale-up. But in the first rollout, it's not that critical because the most critical thing is to create a bigger domain. When you look at the extended memory, I view that as the kind of additional optimization you put on top. Because just doing extended memory without optical scale-up is not really going to get you where you need to be in terms of performance. So it's kind of a step two. But it's a very important step two because it does allow you to kind of decouple the KV caches to this extended memory and this capacity versus bandwidth trade-off that is currently a problem in high bandwidth memory, right? And so it allows you to do that very effectively, but it has to be on top of a technology that has very low latency natively. And for example, that would be DWDM kind of technology where you have NRZ signaling, so you don't have as much, you don't have to put a heavy FEC on top of photonic link, etc. But I would say for that to happen, you first need to integrate the optics in a GPU for scale up and make sure that is exercised. And then a second step would be the extended memory. Yeah.
So how long are we having to wait for this? This is a 2030 thing. I know our talk, when we talked earlier, we were thinking 2028, but it sounded like a little further out than that.
Oh, I think we are looking at that as kind of like a half a generation to a generation after the first insertion. So, Erez and I talked about it at TSMC OIP, for example, as DWDM being kind of a fast follower. to the CWDM kind of initial deployments. And I think you'll see something like a year and a half at most kind of offset between the two.
I read since it seems though he brought you up to, finish his thought.
I think that there are two factors to answer this question. First is what is the roadmap for the memory vendor? And today we see like the move from the HBM3 to 4. If in the past, I would say that we could not have like more than 10 gigabit per pin. Today we see like 12 and maybe even 13 gigabit per pin for like a memory vendor. And also the capacity go up. We see like more flows of HBM, like if the past it was 8, going to 12, going to 16. So basically there is also like a move, right, in the memory market. It's not a stable market. This is one factor. The second one is actually we see the models, right? There are new models for training and there are new models for inference. So I think that there would be in time like an inflection point that once the scale-up network will be fully deployed over optic and the memory would stall, then would be the point that actually people will have already trust in the CPO and the optical network. Then they will start to use that to innovate around the memories as well. But I fully agree with Vladimir that the first wave would be in the scale-up network, and the memories will keeping their own internal roadmap, like we discussed a few seconds ago. And then when memory would stall and the CPO will be there, then we will see CPO going to be integrated, like with the memory solution as well.
Otto, what do you think? And forgive me for not knowing. I can't remember if you do CXL extended memory chips or not, but
Yes.
do you? I assumed you did. I thought you did.
I think this is a very sensible view. See, this idea of having a disaggregated memory pool that you can access anytime you want and allocate it is fabulous. It's almost our ideal world, and it's very exciting. Okay,
it's a memory sand. Of course, it's going to be just fine. Yes, that's how we're used to thinking about things.
Yes, but now, if you want to enable this in a true disaggregated optical way, I'm going to go back to my 3 pillars, right? The technology pillar, the advanced packaging flow and test pillar, as well as the supply chain pillar. All 3 of these change in a subtle way. Okay, they actually enter a slightly different optimization space. It doesn't look like it at a very high level, but when you go deeper, a memory interconnect requires slightly different optimization criteria than a scale-up interconnect. Okay, all the way from latency to the fact that, and I think Vladimir alluded to this, now you need lasers with many wavelengths of WDM that you probably didn't need in your at least first or second round of scale-up networks. So you are subtly changing the optimization space of each of these 3 pillars. Okay, so in a pure developmental sense, it's very prudent to say, let us mature the scale-up platform first. Okay, and then take it to memory. I wouldn't be surprised if someone pushes the memory harder and tries to leapfrog this, no doubt. But one or the other has to happen first and gain stability, and then the other one can happen very quickly. Okay, but they are different in subtle ways on all of those 3 pillars.
I'm worried about manufacturability, affordability, reliability, and serviceability. So lump them all together and, we'll work backwards. Can we get all of those things sorted fairly quickly, to simplify it, so that we can get to the point where we have scale-up networks and then the compute engines and then the extended memory over the timeframes that we think in the volumes that we think. So, I'll work backwards. Audit, you go first, and then we'll go back.
Let me pick one that I think is important for actual deployment and speed of deployment, which is, the many are technical, but at the end, the value chain has to deliver the value. So you have to afford it. Okay. So, there's a lesson to be learned from scale-out networks. And we ignore those lessons at our peril. What happened in scale-out optics is that this, and I previously alluded to this ability to say that this bandwidth distance product truly demands optics, and having very large customers on it for it put pressure on innovation on cost. Okay, so there was innovation on cost, there was improved efficiency.
There was wait, I'm going to interrupt you for 1 second. There was defiance, absolute defiance on cost. The IEEE proposed a certain 100 gig way of getting 100 gig, and they said, no, not good enough, and we'll make our own standard. Thank you. I love that. Go ahead, continue.
But you see, there are many views of, the influence hyperscalers had on scale-out optics. In my personal view, it was an extraordinarily positive influence.
Yes, very much so.
Because they prompted the innovation on cost, they prompted the improvement on efficiency, okay, as well as maturing all of the margins in the value chain, okay, to a sustainable level. Now, it's not that there weren't massive accidents during this process. Okay? There were people that lost money. There were people that went out of business. So I think it's important to avoid that kind of, syndrome as we do scale-up optics. But the fact remains that the maturity of that ecosystem is reflected in a very pure cost roadmap, which is actually affordable at the cost of ownership level. Okay. So as we try to introduce scale-up optics, firstly, it has to be looked at a cost of ownership level. Hopefully nobody's going with optical chiplets and copper chiplets and comparing their costs. Okay. The second one is innovation must happen on costs. There has to be maturity of and efficiency in the whole chain. Okay. I would bring up another aspect of cost as well, because it's not just the cost of the element. Think about it. If you're integrating a rack with CPU optics, this is a multi-million-dollar rack, okay? And someone's got to integrate this rack. And then someone's got to test this rack. And when they test this rack, a single strand of fiber has a dust particle in it and the whole rack fails, okay, locking up millions and millions of dollars. So I would argue that innovation in cost can even come from things like the software at the rack level, okay? How does that software configure? How does that software diagnose? How does that software remediate for that rack to keep working as we integrate so many strands of fiber into complex optical backplanes and optical scale-up networks? Okay, there's the basics of the cost of the element, but there's also the cost of delivering that value to the end customer and the consequences of not doing it right, which are like our value stack needs to take care of.
All right, Erez, your turn.
We cannot address one of them on top of the other. The reason being is today that hyperscalers are running like huge fleets of servers, AI servers, and huge fleets of racks. And only when all of these aspects are going to be ready, then we will see like new racks joining to these fleets. If one of the domain is not ready, the meaning of that, the new system cannot join the fleet, because these guys are not talking about innovation, about like breaking new technology. At the end of the day, they need to deliver, they have a business to run. And only when all of these aspects are going to be mature, then we will see like the new CPO rack joining to the fleet. Otherwise, it will be like large scale in a lab. It will be experimental. It will be like for testing, but it will not going to be like real products. That's my very short answer about this one.
Vladimir, what do you think?
I think architecturally, you need to design a system for these things. Example in CPO that has been kind of adopted as a default, Ayar definitely kind of spearheaded that view, was that, let's say, the laser has to be remote, right? So now you have essentially ELSFP, this kind of thing up here becoming a de facto standard for these applications, where you can do engineer that laser so that both the laser and the chiplet itself actually in a kind of a software defined fashion, kind of connecting to what Adit was saying. These things have to be highly transparent to software in terms of telemetry and health, configurability, but they also, on the laser side, it needs to be pluggable. So the laser is pluggable in the system. Its reliability profile, actually the latest kind of studies that Meta has done show that laser actually not kind of the limiting factor in these type systems anymore. But still, compared to the let's say mean time to failure of just silicon chips and engines, it's still higher up. So you want it to be kind of a pluggable form factor, compatible with liquid cooling and these types of things. But then on the chiplet side, you do have risks like fiber, right? So detachable connector has basically evolved as kind of a de facto standard there, also to address these types of things. So I think those physical features coupled with the architectural elements of both the laser module and the chip that allow this software overlay and supervision, predictive link maintenance, I think those are the key pillars based on which we're going to be able to scale these things.
Anybody want to pipe up? Any final thoughts?
I think that we are lucky to live in such an amazing environment with so many innovation and so many technology. You never have one boring moment. That's great.
It's not boring, that's for sure. The engineering challenges always seem insurmountable. That's the funny thing. Like 20 years ago, things that we think of as commonplace seemed impossible. So, engineers, all credit to engineers. They're just incremental work, sometimes truly breathtaking work. And here we are, We'll have to leave it there. And right now we're going to go to the live Q&A. All right, let's get to some questions here. Let's take the first one, guys. What are your thoughts on the pluggable liquid-cooled 12.8T XPO effort that we heard about multiple times at OCP 25? I feel like this could make CPO less desirable. Vladimir, go first.
Look, the densities in those types of solutions, if they come to fruition, which is kind of dictated mostly by the copper connector into that type of module, are actually comparable, slightly lower than what's being asked of the CPO in the package, but high enough that they require a similar type of optical engine. And so I see that more as a kind of a potential proving ground for the optical engines that will go into the GPU, or in applications where kind of the risk sensitivity is higher, kind of as a first step before you go into the MCP. But we definitely see it as an additional market opening up for us.
Is that intentional? I mean, did they kind of set it up that way on purpose?
I think you can see this as kind of a de-risking or evolution of technology, but definitely increasing the levels of integration that are required, basically, of optical engines.
Otto, what do you think?
Yeah, I think so. It is catering to some path dependence, so it allows people to stay with pluggables in some way. And then it's also increasing density and obviously, even if you were to do this at 200 gig per lane, you now have to yield a 64 lane module. Okay, so it's not necessarily trivial, but as long as the system can tolerate the power and the density, it's sort of an intermediate step. I think it goes back to that question of, have we properly projected the existing technologies forward? And secondly, are we investing our time in a way that's sufficiently future-proof, right? So it would really be the trifecta of these things that will determine that. But it is a very, depending on how this connector shapes up and depending on how the modules are able to, let's say, port all the CPO work into the module, it would be interesting to see how that pans out.
Rez, you agree with that?
Yeah, I think that this is like a secondary market. At the end of the day, the target of the CPO is to shorten the copper channel. And once we bring the CPO in, then there is a lot of gain. But definitely it's like a secondary market. And I fully agree with what was said here.
All right. We've got two questions that are kind of big theory questions. So I'm going to read them really quickly. Here's from one attendee. I've been involved in optoelectronics since the 1990s. Packaging and device costs have been an impediment for literally decades. Chip scale packaging was a dream before the turn of the century. What is the innovation that is causing this to come to fruition now? Has the value, racks, data centers, just gone up and the cost has not gone down? And then we have another one here asking us to have a deep answer. So I think we can do that. The costs for packaging are really high compared to component costs. Contract manufacturers cannot package with the high yield without enormous capital expenses. They cannot achieve ROI without known good die. So there are many barriers to packaging OE devices. How will AI data centers fund the contract manufacturers to package at scale to drive down cost? How will fabs produce known good die to reduce the risk for the contract manufacturers? Thought I'd go first, but let's really hear about how this, because this is the test, right? We were talking about this already, but it's not just having the device, it's that whole chain of value that ends up in a known good product shipped to a customer who's going to use it and be delighted with it.
This is a super important question. Yes. In silicon photonics, there's and in optoelectronics, there's often an adage: you shouldn't design a package for your chip or device. You actually should design your device or chip for the package. Okay, so I would say three things about that question. The design for the manufacturing flow has to start from the ground up. Even devices, subsystems, systems, and full chips have to be designed while keeping the full manufacturing flow as well as rack integration in mind. Okay, so that's the first extraordinarily important piece. If you look at it in a more general sense, you could convince yourself that this, a chiplet consists of an electronic IC, a photonic IC, and an optical connector and a packaging flow. But disingenuously suggests that you can make this out of Lego pieces. Okay? So what it really is that every single piece has to be designed with this packaging flow in mind. Okay? The second thing is a reasonable ownership of the whole flow. Okay? You cannot disaggregate this flow to the point where there's different pieces of ownership and different levels of accountability. Okay? Because at the end of the day, that design, the way it's tested, the way it's integrated into the packaging flow, all interact very deeply. Okay? So there has to be, let's say, a clear owner and accountable party for it.
Which is, by the way, why we see Marvell and Alchip and Broadcom doing so well on custom accelerators. Somebody's got to be the one who's the throat to choke.
Yes, the throat to choke and maybe the neck to grab, which is a bit less violent, perhaps. It all right in every single packaging flow. You have to design for that. You have to put in a design for testability for that, but you also need a software layer. And that software layer, once again, to double click on that, needs to take care of three things. It needs to configure systems and racks. It needs to diagnose when there's an issue, and then it needs to remediate them. Okay. So I think a company that can truly provide everything all the way to that rack level integration and then govern the entire flow from the design through the manufacturing, that's what's critical to addressing this.
Vladimir, that seems to argue for integrated stacks, and we're seeing them emerge. So, it's happening, right?
Yes, and look, you will always have a few completely integrated stacks or as much as possible, and then you'll have other parts of the ecosystem start forming. And you mentioned several XPU kind of design services, also kind of verticalizing in a certain portion of that domain, again, to be able to provide a more complete full service to the volumes that the hyperscale data centers need. Right? And that's kind of naturally evolving. It's a few companies that are making a full vertical because they have enough volume to push, and then there is the ecosystem forming around that will leverage that as well.
Erez, wrap us up on this one. You can get deep. Go for it.
I would say that you start the question with asking about the innovation. Why now? So I think that innovation has a reason. Innovation is not coming like for free. And I think that the AI industry now is coming to like an inflection point. What is this inflection point? Basically, a process cannot give us as much as we want, right? And then we need to go to advanced packaging. I/O bandwidth is actually stalled. Memory capacity or memory shrinking is on stall. So basically, the industry need to find different ways how to keep pushing like more bandwidth, more performance under the same package or under the same system. So the way to go was to go to chiplet, and in order to accommodate chiplet, we need to go to the interposer. And now, after the frequencies of the SerDes is going up, we are trying to go for optic. But I think that what we see is that the industry is not like trying to use so many manufacturers at the moment to do like one foundry we will do the silicon, one foundry will do the interposer, and third OSAT or third CM will do the packaging. We see that everything is going under the same roof, and that goes with like the one neck to choke or the other phrase, right? And at the end of the
One
day,
hand to shake really hard.
yeah. And we see that basically like TSMC start to push like for the optics and not get like a third party one, because we all understand that this is a very complex integration. So once you have all the components under the same roof, I think that would haze the integration process, and it will be easier to get ongoing with the market with these kind of innovations.
I can leave it at that, guys, if you don't want to spend more time on this and go to the next one. In traditional copper networks, we understand failure modes well, bit errors, signal degradation, etc. What are the unique failure modes for optical interconnects, and how do systems detect and respond to them? Can a cluster gracefully degrade if some optical links fail, or is it more binary? Erez, you want to go first?
So basically, I think that we are going to have in this new environment like a new component like the fiber attachment or maybe external lasers. So we don't know exactly how to predict, but we know that the technology is going to get mature as it will get going. Meaning that if you ask me what is going to be the failure rate for this fiber attachment for the other fiber attachment, I really don't know to predict that. But I know that like any other problem in this industry, when there was a need, there was so many smart people that actually sit down and in reasonable time solve the problem and get it to be mature, right? Look about advanced packaging, about the huge progress with the HBMs and so on. So I think it's goes under the same category.
Audit, go ahead.
Yeah, I think it should be separated into unique optical failure modes at startup, let's say at rack construction, versus reliability over time. I think in terms of reliability over time, there are a number of new components and interfaces that have to be properly tested against standards that I think have to evolve for this specific use case. Okay, so in some ways we have to force more stringent qualification requirements on this construction. In the beginning, I go back to my earlier point. As you build the rack, there will be numerous optical specific failure modes that will have to be covered, both from the perspective of design as well as the software. I think the word graceful degradation was used. I'm not sure there's anything that graceful about degradation, but that suggests very much something like laser wear out. To the extent that in these architectures, lasers have been disaggregated from the major heat source and made modular, that should actually cover a major piece of that. But I think the step that has to be taken, or maybe it's been already taken to some extent, there is a tremendous amount of scale out data for optical failure modes now. Both in terms of at startup and reliability, and that has to be properly projected forward into this, while also accounting for the fact that we are going to have lots and lots of fibers in a rack infrastructure and lots of connections. Yeah.
All right, Vladimir, you have to finish it for us. I think we're over time, but we're going to let you have the last word on that.
No, absolutely. Given kind of the scales we're talking about, both in terms of number of lasers and number of optical lanes on the optical engines, you absolutely have to design these types of features into these systems. And I did touch on it a little bit earlier. We're talking about telemetry down to every link, every lane, down to every laser diode that's in the module. You have software configurability and telemetry feeding up the firmware and system software to expose these things so that the software can be configured in a flexible way to inspect, detect, diagnose, and then take appropriate actions. I think we're basically building these as software configurable entities that you can manage. And that's the only way to be flexible for different rack infrastructures and different deployments.
All right, we're going to have to end it there. I'd like to thank our speakers. Thank you for attending. And I also wanted to let you know that this recording will be available in a few days. If you didn't get to watch all of it, or you want to share it with your friends, and there's a very good chance I'll put it on the next platform as well. So thank you all for attending.
Thanks, Tim.
Thank you. Thank you, Tim.
Bye-bye.